All right, hello class. Today or in this video I should say, we're going to start on section 3.2, which is on open and closed sets. And this is going to be our first foray into really formalizing what we mean by open and closed. So far, really all we've had is what we mean in terms of intervals. So in terms of intervals, right, we know that, say, a to b, or a to infinity, or negative infinity to b, these are all open. Whereas on the other hand, when we close off the brackets, so ab brackets, or a bracket to infinity, or negative infinity to b bracket, these are closed. And all we really have right now to signify the difference has to do with what kind of inequalities we're talking about. So for these open ones, we're essentially saying that all the x's are strictly between a and b, while for the closed ones, the inequalities have an or equal to. Now, this kind of definition doesn't really help us when it comes to things like the Cantor set or other strange sets we might run into. So we want to formalize these definitions so that we can talk about whether any particular set is open or closed. So for example, is in, right, this set 1, 2, 3, 4, etc., is this open or closed? Well, it's not an interval, but it may share some of the same properties as an open or closed interval might. All right, so we want to broaden the way we categorize sets, so it's not just restricted to intervals. All right, so we want to broaden our categorization of open and closed sets. To include things that aren't just intervals. Okay, and so we will do that first. I think the easier one to wrap our heads around probably is open sets, or are open sets. Okay, so let's give the definition of open set. Okay, so a set, and I'll call it O. Always have trouble doing like a capital O. So a set, which is say a subset of the reals, is open if for every element in the set, so if for all x in O, okay, there exists an epsilon greater than 0 such that v epsilon of x is completely contained in O. So what does this mean? Well, what it's basically saying is that for every element, so I'll write i.e. for every element in O, there's an epsilon neighborhood around that element also completely contained in O. Okay, in other words, if x is in O, then there exists an epsilon such that x minus epsilon to x plus epsilon is also contained in O. This is what we mean by open. Okay, so let's take a look at some examples of what would be considered open. Okay, so the first example is our open intervals, right? So the interval, let's call it I, which goes from A to B, is open. Okay, since for any number or any value inside this set that we choose, so let's say this is our, this is our open interval, A to B. All right, any x I choose, I can maybe not easily, but I can always choose an epsilon neighborhood that is still contained in the interval. So if, say, I'm looking even at something like really close to B here, right? So let's say this is Y, which is approximately B, but still less than. We can always still zoom in as close as we want, and say that our y is right here, and then choose, say, an epsilon smaller or small enough so that this interval y minus epsilon to y plus epsilon is still contained in the interval itself. Now, on the macro level, it might look like this. You can probably barely see that. Okay, but the whole idea of an open interval is we can get as close to B as we want, right? We could even pick another value here, and as long as we choose an epsilon small enough, we can always put an epsilon neighborhood around that element back into the interval, and it'll still be there. Now, if we wanted to give a formal proof of this, so if we wanted to prove this, it's actually, well, it's kind of this same idea here. All we're going to do is we'll let x be in the interval A to B, right? So, in other words, x is trapped between A and B, and we will have two possible distances we could pull from. There's either the distance between A and X, or there's the distance between X and B. Okay, so we're just going to choose the smallest one. So let epsilon be the minimum of either the absolute value of A minus X or the absolute value of X minus B. Okay, now we could actually, so this is going to pick the exact distance. We could also chop these in half if we wanted to. So we could take the minimum and then cut it in half if we want to be really rigorous. Okay, and so depending on which one is the smallest, then we're going to cut it in half and get something even smaller. So then v sub epsilon about x is going to be x minus epsilon to x plus epsilon, and just based solely on definition, this will be contained in A to B. All right, therefore, the interval a to b is open. All right, now this argument will work, I'll say a similar argument will work for a to infinity open. But instead of choosing the minimum, because it's clear which the minimum is going to be, you wouldn't do the distance between x and infinity. You would just choose epsilon to be the distance between x and a. And you can get the epsilon neighborhood within this interval. And then similar for negative infinity to b. Okay, this also gives us that, so consequently, all of R is open, right? Because for all x in R, we don't even have to specify an epsilon. Any epsilon will work. We can choose any epsilon, and x minus epsilon to x plus epsilon will be contained in the real line. Okay, so that does tell us that R is open. Now, you may be wondering, well, how about unions? Like when we have things like, all right, negative infinity to -1, union -1 to 3, union 3 to 5, union 9 to infinity. Okay, all of these are open, and we're taking a union of open sets, open intervals, so does that make that open? And the short answer is yes. And instead of just doing it for this particular example, this does lead us to one of our next theorems, where we'll do this just in general and just prove it once, and then we can utilize it going forward. Okay, so this brings us to theorem 323, which has two parts. The first part says that the arbitrary union of open sets is open, and part 2 says the finite intersection of open sets is open. Now, what the arbitrary union means, it basically means that arbitrary basically means it's true for finite, countable, and uncountable. Okay, so in other words, we can take an arbitrary collection, either a finite number, countable, uncountable, however many. You take that full union of all these open sets, you'll get back to an open set. Of course, 2 is just saying that the finite intersection of open sets is open. So this means that it won't always be true if you're talking about a countable intersection or an uncountable intersection. We can only guarantee it to be true for a finite intersection. So essentially, what this bit means is that if we have a collection of open sets, and usually for the arbitrary thing, they'll use, they won't use n, like O sub n. They'll use something like O sub sigma, where sigma is in some arbitrary set lambda. Okay, sometimes they'll use lambda as well. Okay, so if each O sub alpha is open, then the arbitrary union of every element, okay, of all of these is open. Okay, now this does carry over to countable, so we can say that n is in the naturals, right? So it's true here, but we can take it further. We can also say it's true for open sets where we index them all the way through the reals. Okay, so you can imagine if we were to take, let's say OX, every OX just took an X and did this. It said X minus 1 to X plus 1, right, for all X in the reals. Then if we took the intersection of all of those, or sorry, not the intersection, the union of all of those, well, the union of all of those is going to end up being R, right? Because we're just taking a distance 2 around every element of X and unioning them all up together. And so you'd end up with a bunch of overlap here, right? So you'd have this, and then you'd have this, and then you'd have every X would give you, right? And you're basically just unioning all those up together. Eventually you'll get the entire real line. Okay, so that's essentially what this part 1 is saying. So it's even stronger than a countable union. It's an arbitrary, in other words, uncountable union. Whereas, strangely, we can't say the same is true for intersections of open sets. Okay, so let's go towards proving all this. All right, and I'm going to clean this up a bit before we get there. Okay, so we'll start with the arbitrary union of open sets is open. So we're going to let O sub, we'll use lambda, for lambda in capital lambda, be an arbitrary collection of open sets. Okay, so we want to show, say this, we want to show that the union of all these arbitrary open sets is open. So to show that it's open, we want to show that given any X in this union, in this final set, so I'm going to call this O, just regular O, we essentially want to show that for any X in O, that there exists an epsilon neighborhood around X completely in O. Okay, so to do that, we're going to start by let X be in O, which is equal to the arbitrary union of these open sets. Okay, this means that for some, well, this means that since this is a union, that means this X is in at least one of these open sets. I don't know which one, but it's in one of them. Okay, so this implies that X is in one of the open sets in the collection. Okay, in other words, i.e., there exists a lambda star in capital lambda such that x is in O subscript lambda star. All right, well, if this is true, we know that this O lambda star is open, so there exists an epsilon greater than 0 such that the epsilon neighborhood around x, which is equal to x minus epsilon to x plus epsilon, is completely contained in O lambda star. Well, this epsilon neighborhood is contained completely in this, then it must also be in the arbitrary union, because the union just takes everything that's already there and combines it all together. Therefore, v sub epsilon about x, so the epsilon neighborhood around x, which is equal to the x minus epsilon to x plus epsilon, is completely contained in the intersection which is our O. And since x was arbitrary, right, therefore O is open, and that completes the proof. Okay, now let's tackle the second part, which is that the finite intersection of open sets is open, and then we'll discuss why it's not true past, or sometimes it's true for infinite cases, but why we can't guarantee it's true for the infinite cases. All right, so how we'll start this is, of course, we're going to let O1, O2, O3, all the way up to On be a finite collection of open sets. Okay, and what we want to show is we want to show that the finite intersection, so k going from 1 to n of O sub k, is open. Right, so we're going to start by picking an x in this O, and then try to show that basically for all x in O, there exists an epsilon, of course, greater than 0, such that v sub epsilon around x is contained in O. Okay? All right, so that's how we're going to start. We're going to let x be in O, which is the intersection k going from 1 to n of O sub k. Okay, if x is in the intersection, this means that x is in O sub k for all k going from 1, 2, 3, all the way up to n. Okay, so it's in every one of these. So x is in O1, it's in O2, it's in O3, it's in O4. Okay, so maybe I should write it, well, no, that's fine. Okay, now each O sub k is open. So for each one, there exists an epsilon k greater than 0 such that the epsilon neighborhood, which here, since I'm having more subscripts showing up, I'll just say x minus epsilon sub k and x2, or 2x plus epsilon sub k is completely contained in O sub k. Okay, but the thing is, since each open set is different, I don't know if it's the same epsilon that will work for, say, 1 that it will for 2, right? So what we're essentially saying is that there's an epsilon 1, and here I will use the v. There's an epsilon 1 for our first open set. There's an epsilon 2 that will work for our second open set. There's an epsilon 3 that's going to work for our third open set, and epsilon 4 that will work for the fourth one, etc., until we get up to an nth one that works for the last one. Okay, now since I have a finite number of these, what I can do is just take the smallest one. So let just epsilon be the minimum of all these epsilon sub k's for k ranging from 1 to n. And since it's finite, I know, one, that the minimum exists, right? Because remember, that's one of the conditions we need to calculate the minimum of a set, right? A minimum doesn't always exist, an infimum does. But since this is a finite set we're talking about, this set of epsilon k's, since it's a finite set, I know the minimum exists and must be greater than 0. And this right here, I'm going to put a star here, this is the part that would fall apart in the infinite case. So this is the step that would fall apart in the infinite case. Okay, because we wouldn't be able to take the minimum necessarily, and if the epsilon k's converge to 0, there's no minimum anymore. The supremum, or not the supremum, but the infimum would be 0, and then you couldn't say that you couldn't make an epsilon neighborhood with 0, right? That epsilon always has to be greater than 0. Okay, so when we let epsilon be the minimum here, then v sub epsilon around x, which is equal to x minus epsilon to x plus epsilon, this will be contained in O sub k for basically all k's between 1 and n. So for every k. Since this is contained in every single k, this implies that v sub epsilon, which is the open interval x minus epsilon to x plus epsilon, is contained in the intersection. Okay, which is our O, and that's it. We took an arbitrary x in our O and showed that there's a epsilon neighborhood around x in our O. This implies that O is open. Okay, so I did explain where it, where the proof would fall apart in the infinite case. However, a stronger thing to do here is to give a counterexample of the infinite case and not just a little statement there. So let me show you an example of a situation where the countable intersection of open sets will not be open. All right, so we want a countable intersection of open sets that is not open. All right, so here's the collection of sets I want to look at. Consider O sub k, which will be the open interval. Let's do -1 over k to, let's do 1 plus 1 over k. Okay, so in other words, we're looking at this sequence of open intervals that goes -1 to 2, -1/2 to 1.5, -1/3 to that'll be 1 1/3, so that will be what, 4/3. So let me be more consistent here. That'll be 3/2, 4/3, -1/4 to 5/4, etc. Okay, so here's my claim. I claim that the intersection of k going from 1 to infinity of these OKs, oh, I didn't even realize I had done that. In other words, the countable intersection of these open intervals, -1 over k to 1 plus 1 over k, I claim that that is equal to the closed interval 0 to 1. Okay, and I'm going to prove that. Okay, so the first direction is probably not too bad. I want to show basically that 0 to 1, and I'm going to call this capital O again, just to save myself some headache. But I want to show that 0 to 1 closed is contained in O, and O is contained in 0 to 1. Okay, so that is going to prove that these two sets are equal. Okay, so this first direction isn't going to be too bad. I'm going to start by letting x be in 0 to 1 closed. So this implies that x is less than or equal, or 0 is less than or equal to x, which is less than or equal to 1. Okay, now if this is true, this implies, well, actually let me do it down here. If x is between 0 and 1, well, 0 is always greater than -1 over k, right? And x is always strictly less, and 1 is always strictly less than 1 plus 1 over k, since the 1 over k is always positive, and this is true for all k in the naturals. I guess I didn't specify that here. This is for all k's in the naturals. Okay, we don't want to be dividing by 0 and all that kind of stuff. Oh, well, in other words, x is, or -1 over k is strictly less than x, which is strictly less than 1 plus 1 over k. And this is for all k in the naturals. This implies that x is in the interval -1 over k to 1 plus 1 over k for all k in the naturals. So x, if it's in 0 to 1, then x is in this open interval for every single k. That means it's in the intersection of all of them. In other words, that means it's in O. Okay, so there's our first step taken care of. All right. Now for the next direction, I'm going to let x be in O, which means it's in O sub k for all k in the naturals. And this is going to be very similar. This implies that x is trapped between negative 1 over k, whoops, and I keep doing that, 1 plus 1 over k for all k in the naturals. Now, by the squeeze theorem, we have that the limit of negative 1 over k is less than or equal to the limit of x, which is less than or equal to the limit of 1 plus 1 over k. Now note, we're doing less than or equal to mainly because when you're talking about limits, they can be greater than each other always, but their limits could be the same, right? So one could always be strictly greater than 0, and the other one could always be strictly less than 0, but both converge to 0. Okay, so that's why when you do the squeeze theorem or anything like this, you do need to account for the fact that they may converge to one another. And this implies that essentially 0 is less than or equal to x, which is less than or equal to 1, implying that x is in the closed interval 0 to 1. Now, we don't necessarily have, well, actually, let me just say that this implies that O is equal to 0 to 1. All right, because this proved the second piece. Now, we haven't proved it yet, but we know that this is closed just from previous information, but let me just claim 0 to 1 closed is not open. Okay, I'm being very careful about saying it's closed in an official sense. We know it's closed just from our previous knowledge, but again, we haven't really established an official formal definition of closed yet. So instead, I'm just going to say that this is not open. Right? It's not open because I can find two elements that will not have an epsilon neighborhood within the set itself. All right, because 0 and 1 are in the open or the closed interval 0 to 1 and will have no epsilon neighborhood. I'll just put in hood around them in 0 to 1. For example, if I take, right, here's 0, here's 1. If I'm looking at 1, any epsilon neighborhood I choose is going to take elements outside of the set. No matter how small I get epsilon, it's not going to, the epsilon neighborhood around it is not going to be completely contained inside the set. So for all epsilon greater than 0, V epsilon around 1 is not contained in 0 to 1. In other words, V epsilon around 1 is not a subset of 0 to 1. Therefore, 0 to 1 is not open. Okay, meaning the intersection of k going from 1 to infinity of O sub k is not open. So there we go. The infinite intersection of open sets are not necessarily open. Now you can create an infinite intersection of open sets that will be open, but it won't be true all the time. So that's what this counterexample shows us. All right, I don't think we have enough time in this particular video to really get into closed sets, so I will save that for the next lecture. We will talk about closed sets in that one, and that one's a little trickier and elicits a lot more complicated examples of what can count as closed sets. Before we do that, I do want to note this little argument I did right here. That is how you would well, this is where the proof that A to B open would fall apart if you closed off one of the endpoints, right? This particular argument, if you chose one of the endpoints, that proof would fall apart. Okay. Anyway, I will leave it there and catch you on the next one. Cheers.